Welcome to myprojectbazaar.com. We will discuss about the product for efficient FPGA and ASIC realization of DA based reconfigurable FIR digital filter. Next we will see the abstract for the product. Reconfigurable finite impulse response filter whose filter coefficient dynamically change during the runtime plays an important role of software in the software defined ratio system. Multi-channel filter and digital up-down converters. However, the well-known multiple constant multiplication based technique, which is widely used for the implement of FIR filters, cannot be used when the filter coefficient dynamic change. On the other hand, a generally multiplier based structure requires a large chip area, consequently enforce the limitation of maximum possible order of the filter that can be realized for the high throughput applications. The brief presents efficient distributed arithmetic based approach for the high throughput reconfigurable implementation of finite impulse response filters whose filter coefficient changes during the runtime. Conventionally, for reconfigurable DA based implementation of FIR filter, the lookup table based DA based FIR filter are required to be implemented in RAM, and the RAM based LUT is formed to be costly for ASIC implementation. Therefore, a shared LUT design is proposed to realize the DA based computation instead of using the separate register to store the possible results of partially inner products for the DA processing of different bit positions. Registers are shared by the DA units. Bit slices different weightage. The proposed design near by the 68 and 58% less area delay product and 78 and 99% less energy per samples of DA based systolic structures of carry save adder technique. The carry save adder technique is used for the ASIC realization of DA based reconfigure FIR digital filter architecture. We will see the flow diagram for the product. The input samples and the error samples to apply the delay unit architectures. The delay unit architecture is mainly based on the register element. The deflip register elements to use the delay adder process. Then the delay element result is applied to the partial border generation unit. The error bit samples is to create the error coefficient manner. Thus, the addition work to the error input bit samples using the partial border generation architecture. The partial border generation addition architectures mainly based on the carry select addition process. Then to apply the shift add architecture block. The partial border generation result is to pass the shift add architecture block. The shift add architecture block is used to the addition the partial border generation results in separate manner. This process is mainly used to the reduce the carry propagation time and to reduce the hardware complexity for the shift add architecture work. Then the shift add architecture result is applied to the delay and adder element. The delay and adder element mainly used for the store the results in register, then to apply the final output results. The final output results to get the delay and adder element. The delay element is mainly used for the deflip register element. The adder element is mainly focused by the LSB and MSB position for the shift add architecture result and to apply the delay and adder unit elements. The final output samples is mainly based on the synthesis and simulation results elements. The simulation results is mainly passed by the binary results element, and the synthesis report is mainly focused by the satisfy the parameter results for the in our architecture. And finally we see the output for the product. First of all, we open our processing folder, then we open the Xilinx ISC project. our program is developed in VHDL language. Then we select the weighted update block to select the simulation work, then to select simulate behavioral model. We run the process for our processing result, then open the Xilinx ISM projects. The simulation behavioral model was completed successfully. Then create the ISM project list. Then we apply the binary input and to calculate the output weighted bits. Now apply the 16-bit data length for our project. Then add the error signal in coefficient manner. Then apply the clock pulse. We can create the programmable process. Just we close the simulation process. Next we go into this implementation work. The implementation work to create the view RTL schematic. Just we run the schematic diagram. The RTL schematic diagram is mainly used to create the RTL diagrammatic representation. Just we double click this diagrammatic representation is mainly used to what are the logical blocks is placed in our weighted filter architecture. Then the technology diagram is represents the what are the lookup table and input output buffers, then wire connections and flip-flop pairs to be applied by our overall weighted filter architecture. Then we go to the design summary result, then the synthesis report. Just we generate the synthesis report for the weighted filter architecture. This architecture results is to calculate the area of the device utilization of weighted filter architecture, and finally we calculate the timing allocations for the latency and delay time calculation for our weighted filter architecture level.